In this video, we're going to talk about how to create a 12-volt DC power supply from a 220 volt AC power source. So the first component that we need is called a transformer, specifically a step-down transformer with a turn ratio of, in this example, approximately 16.9 to 1. What this transformer will do is it's going to take a 220 volt AC signal or AC power source and convert it to a 13 volt AC power source. This is the primary voltage on the left. On the right is the secondary voltage. The ratio between the primary voltage of the transformer and its secondary voltage is equal to the ratio of the primary turns to the secondary turns. So the number of coils of wire on the left side is 16.9 times greater than the number of coils of wire on the right side. So with this particular transformer, we can get an output of 13 volts AC or alternating current. Now the next component that we need is a diode. A diode is a semiconductor device that allows current to flow in one direction, but prevents it from flowing in the other direction. So this is current flowing in reverse bias mode, and in this case the diode will be off. But in forward bias mode, the diode is on. So the diode will allow us to convert an AC power source into a DC power source. It converts alternating current into DC or direct current. Now the circuit that you see on the screen is called a full wave bridge rectifier. And before we go into that circuit, let's talk a little bit more about the diode. The left side of this diode is known as the anode. The anode is the positive terminal, and on the right side, that is the cathode, which is the negative terminal. Now, when building a circuit like this, looking at the diode, you need to identify the part with the silver strip. That is the cathode of the diode. The part that lacks the silver strip is the anode. So make sure you understand that difference. Now let's call this point A. This is going to be point B, point C, and point D. Now let's label the four diodes that we have here. So we'll call this D1, D2, D3, and finally D4. So at the input, which is here, we're going to have an alternating signal. So we're going to use a sine wave. And let's talk about the positive half, or the positive half cycle of this sine wave. When we get that positive half cycle, one side of the transformer at the output, that is the output of the transformer, not the output of the actual circuit. One side is going to be positive, the other side is going to be negative. Conventional current will flow from a high potential to a low potential. So the potential at the negative terminal of the transformer, we're going to give it a value of 0 volts. And at the positive terminal, we're going to say that is 13 volts, based on the specific type of transformer that we're using. So current is going to flow from the positive terminal to the negative terminal. Now we're dealing with conventional current, which is opposite to the direction of electron flow. Keep in mind, electrons in a circuit flow from the negative terminal to the positive terminal. But most physics textbook will use the direction of conventional current flow. So current is going to flow from the positive terminal to point A, and then it's going to flow through D1, because D1 is in forward bias mode. It can't flow from point A to point D, because that is in reverse bias mode, and D4 is going to block any current going in that direction. So that's not going to happen unless the voltage is very, very, very high. As current flows from A to B through D1, it's going to flow through this resistor and then to point D. Now from point D, it's not going to go back to point A because it's going to make no sense. So the only logical place it can go to is through D3 to point C, and then back to the negative terminal. So that's going to be the flow of current during the positive half cycle of this circuit. So we're going to have a positive voltage at the top of the resistor and the negative voltage at the bottom, because current will be flowing in this direction. Now let's talk about the voltage potential in each of these 4 points. At point A, the potential is 13 volts. Now what do you think it's going to be at point B? A silicon diode has a voltage drop of around 0.6, 0.7 volts. A germanium diode has a voltage drop of about 0.3 volts. So if we use a silicon diode, the potential at point B will be, we're going to say 12.4. So we're going to use a 0.6 volt voltage drop. Keep in mind, some will be 0.7, and you may find a few at 0.8, depending on how much current is flowing through it. But let's use 0.6. Now, the potential at C is 0, and at D is going to be 0.6. So as current flows from point A to point B, we have a 0.6 volt voltage drop. And then when it reaches back to point D, the potential is 0.6 volts. Notice that it's not going to go from point D to point A, because conventional current will not flow from a low potential to a high potential. It's not going to go in that direction. It flows from a high potential to a low potential. And that's why you want to understand what the potentials are at each point. Now it will flow from point D to point C, because we're going from 0.6 to 0 volts. So the potential across the resistor is the difference between 12.4 and 0.6 volts. So we have a potential difference of 11.8 volts between or across that resistor. Now we want to create a 12 volt DC power supply. And so we don't want 11.8 volts across the load resistor. Let's call this RL. What we want is 12 volts, not 11.8. So instead of using the silicon diode, what we're going to do is use the germanium diode. So if we were to use the germanium diode, the potential at point B will be 12.7 volts. And C is still going to be at 0 volts, but D is now going to be at 0.3 volts. So the difference between point B and D is 12.7 minus 0.3. So right now we have an output voltage of 12.4 volts, which is about 12. So that's reasonable. We can work with that. Now let's talk about the negative half cycle of this DC power supply. So during the negative half cycle, the polarity across the transformer will be reversed. So it's going to be negative at the top, positive at the bottom. So this is going to be a plus, and this is going to be a minus. So the potentials will change. So the negative side, we're going to assign it a potential of 0, and the positive side, a potential of 13. So current is going to flow from the positive terminal to point C. So point C is at 13 volts. Now, it's not going to go through D3 because it's in reverse bias mode. D3 is going to block that current. So this time, it's going to go through diode 2. So diode 2 is on, while diode 3 is off. Now it's going to flow through point B, through this resistor. Notice that it's going in the same direction as the positive half cycle through the resistor, from positive to negative. So that doesn't change. And then back here to point D. Now it's not going to go back to C, because that's like going in a circle. It's going to flow through D4 to point A, to the negative side of the transformer. So D4 is on, while D3 and D1 are off. The potential at point B will be 12.7 volts. And then at point D is going to be 0.3 volts. And then 0 volts at point A. So you can see why D3 is off. It's not going to go from 0.3 to 13. Current will always flow from a high potential to a low potential. In either case, during the positive half cycle and during the negative half cycle, the current is flowing in one direction through the load resistor. That is from the top to the bottom. And that's what we want to create a DC current, a direct current. Direct or DC current flows in one direction, whereas AC current, alternating current, flows in both directions. With an AC power source with a frequency of 60 Hertz, the current reverses 60 times per second. But to create a DC power supply, we want the current flowing in one direction, which is what we have now. Now let's talk about the voltage at the output. At the output, what we have is a DC supply or a DC voltage that looks like this. It's not constant. Basically, this portion of the graph was flipped to the top. The question is, how can we take this pulsating DC output and convert it into a nice, steady DC output? One way to do that is to introduce a capacitive filter. So by adding a capacitor that is parallel to the load resistor, we can reduce the fluctuations in voltage at the output that we see. So instead of having a pulsating DC output that looks like that, the output will now look something like this. The fluctuations are less, and these fluctuations are known as the ripple voltage. Now, by increasing the capacitance of the capacitor, you can decrease the ripple voltage. So the greater the capacitance, the more the output will look like this. It won't be perfect, but it will be, for the most part, fairly steady. So it's important to introduce a capacitor at the output. Now, another thing you have to take into account is the surge current, and that is when the capacitor is charging, because it's going to charge from 0 volts to the potential at point B. The potential at point B is 12.7, and at point D we said it's 0.3. So the capacitor will charge to 12.4 volts, the difference between point B and D. So while it's charging, a lot of current will be flowing through this capacitor. Now keep in mind, there's no current that actually flows in between the dielectric of the capacitor, because there's an insulating material there, but the capacitor is charging. Electrons are being pumped from one side of the capacitor to the other side, and so you have a large current flowing through these wires here for a short period of time. So to reduce that surge current so you don't burn out your diodes, one, you can use a diode that can handle a very large amount of current. Some diodes can handle 1 amp, others can handle 10, and there are some that can handle 100. So you may want to consider using diodes that can handle a large amount of current, or you can add a current limiting resistor. So we can put a series current limiting resistor, which we'll call RS. Now the value of RS will vary based on how much current you want to flow, that you want to have flowing in a circuit. So if you want to have a large amount of current flowing in a circuit, use a small value of RS. Now, as you increase the value of RS, the output current will decrease. In addition to that, the output voltage will decrease as well, because these two resistors, the load resistor and the series current limiting resistor, acts as a voltage divider. So the output voltage will be equal to RL divided by RL plus RS times the potential between points B and D, which in this example is 12.4. So if you're going to use a series current eliminating resistor, to keep the output voltage as high as possible, you want to make sure that RL is significantly larger than RS. So let me give you an example of some numbers. So let's say that RS is 10 ohms. It's relatively small. And RL is a kilo ohm or 1,000 ohms. So the output voltage will be 12.4 times 1,000 divided by the sum of these two, which is 1,010. And so the output voltage won't change by much. In this case, it's going to be 12.28. So by making sure that the load resistor is significantly higher than RS, the output voltage will still be above 12 volts. Now, to determine the amount of current that will be flowing through the series resistor, you need to find a potential between point B and let's get a new point, point E. Now we want the output voltage to be 12. Right now it's 12.4. So we need point E to be at 12.3 so that the difference between E and D is 12. So let's say E is at 12.3, B is at 12.7. The voltage across RS is the difference between the potential at E and the potential at B. I mean, B minus E rather. And then we need to divide it by RS to get the current. So it's 12.7 minus 12.3 divided by 10 ohms. So the current that's flowing through that resistor is only 0.04 amps. It's very small. So the value of that resistor is relatively high. Now, if we were to drop RS to 1 ohm, the current flowing through it will be 0.4 amps or 400 milliamps. Now, we need to think about the worst case scenario. That is, if we have a short across the output. That is, if the load resistor drops to 0. If that happens, the potential at E and D will be the same. So the voltage across RS will now be 12.7 minus 0.3 or 12.4. So the maximum current flowing through RS will be 12.4 volts, the potential between B and D, divided by RS, 10 ohms. This is the value you need to pay attention to. So this will be 1.24 amps because you need to take into account if there's a short circuit at the output, because this is going to be the amount of current that's flown through the diodes. So if you have a diode that can handle only 1 amp, it could burn out if there's a short circuit. So for this example, using a 10 ohm series current limiting resistor, we want a diode that can handle 5 amps or 10 amps. We want to make sure that if there is a short circuit, the diodes can handle the surge current. Now there's one more element that we need to add to the circuit, and that is a zener diode. A zener diode acts as a voltage regulator. It can help maintain a constant output voltage for this circuit. And it's designed to work in reverse bias mode. Now, the zener voltage that we want to have for the zener diode is 12 volts. Ideally speaking, we need to set the right current flowing through it so that the voltage drop across the zener diode is 12 volts. Now, let me take a minute to explain how this is going to work. So I'm going to use the voltage between points B and D. So let's go with 12.4 volts. And let's put a zener diode across it. The zener diode is going to draw current from the power source. And whenever you draw current from a power source, the voltage of that power source will decrease. So using a 12 volt zener diode, it's going to bring down the voltage from 12.4 to 12.3 to 12.2 to 12.1 and eventually to 12. When the voltage drops below 12, the zener diode will no longer draw any more current away from it. So it's going to draw enough current to bring down the voltage from 12.4 to 12, and the remaining current will flow to the output. And so that's how the zener diode works as a voltage regulator. It brings down the voltage to a certain point. And this is in an ideal situation. Keep in mind, these devices are not perfect, and the actual voltage drop across the zener diode is dependent on the amount of current flowing through it. So when you're purchasing a zener diode, you need to look at the specification sheet, because there is a certain zener current that, if flowing through the zener diode, its output voltage will be approximately 12. Now, if the current changes, the voltage doesn't change too much from 12. It might change from like 11.6 to 12.4, but for the most part, it's going to be centered at 12. So when looking at the specification sheet of the zener diode, you want to look for a number called the zener current. And you want to design your circuit in such a way that the zener current is flowing through the zener diode so that the zener voltage will be 12 volts across the diode. And so you may need to adjust your series current limiting resistor, and also take into account the load resistor, and set it in such a way that the zener current flowing through the diode will lead to a zener voltage of 12 volts. So now you know how to build a 12 volt DC power supply from a 220 volt AC power source. So that's it for this video. Thanks for watching.